UIU Mars Rover team is excited to introduce Axios, our latest generation rover designed and developed by a team of passionate and skilled students from United International University. Our journey began in 2021 with a mission to push the boundaries of space robotic research in Bangladesh and compete on the global stage. UIU Mars Rover team consists of talented individuals organized into 6 specialist sub-teams: science, mechanical, electrical, aerial and communication, software and navigation, media and branding. Our goal is to innovate, inspire and make a mark in the field of planetary exploration. In 2022, 23 and 24, our team secured first place in Asia and consequently 13th, 9th and 5th globally at the University Rover Challenge at Utah. And in 2023 at the Anatolian Rover Challenge, we secured third place globally and first in Asia, proving our excellence on the global stage.
This year, our rover Axios is built differently than before. We have changed the overall structure of the main chassis. The rover's overall stability and balance have been improved by lowering its center of mass, which greatly increases its capacity to traverse rough and uneven terrain. The rover's kinematics are optimized for difficult conditions with the integration of a rocker-bogie suspension system and a rear differential bar, which allows smoother and more controllable movement. To further improve the rover's performance, we have also repositioned the power and control system to get an ideal weight distribution. The rover can now comfortably climb inclines of up to 40 degrees and navigate uneven terrain with ease because of the newly built suspension system and redesigned 3D-printed wheels. A significant improvement has been made to the robotic arm, which now includes high-precision brushless motor-driven wrist actuators and lightweight carbon fiber tubes. These developments allow for more precise movements by improving the rover's agility and operating precision. The rover's stability and versatility over a range of terrains are strengthened with the inclusion of a thrust bearing and enlarged wheel mounts. In our effort to test Axios limits, we have created difficult and demanding test courses that evaluate how well it can retrieve and move things in harsh environments. The robotic arms with 6 degrees of freedom is designed to carry a variety of payloads from small items to weight weighing more than 10 kg. It can handle objects like boulders, hammers and screwdrivers with precision. With a lightweight semi-differential design, direct-driven motors and a planetary gearbox for improved control, we unveiled a substantially improved wrist mechanism this year. Because of its adaptability, the arm can do complex operations including opening drawers, putting in and taking out caches, painting with a brush on different surfaces, and dealing with devices like USB drives, electrical sockets, push buttons, switches, joysticks, screws, and keyboards. A pressure-sensitive center-aligned parallel sliding end effector at the core of its grasping mechanism guarantees accurate handling of delicate and complicated items. Together, these advancements improve the rover's capacity to adjust to unpredictably changing terrain, overcome complex operating difficulties, and do difficult jobs accurately and effectively.
The rover begins its mission at the designated landing site selected through comprehensive geological mapping. Immediately upon touchdown, a wide-angle panorama camera captures high-resolution images of the surrounding terrain. These panoramic and stratigraphic photos allows us to assess geological formations and identify the structure of the area based on visible layers, sediment disruptions, and weathering patterns. We have developed an advanced sensor fusion system to assess atmospheric and soil parameters, identifying suitable locations for habitability. The rover records 7 key atmospheric parameters including temperature, humidity, as well as 7 vital soil conditions such as pH, moisture, and temperature at a depth of 10 cm. Using combined geological and sensor data, the rover selects and navigates to the first sampling site within the region identified in our pre-mission science report. Subsequent chemical testing is conducted in our enhanced wet lab Bifrost, which features clear indicators for remote operations and controlled lighting to optimize visual clarity via camera feed. The wet lab is thoughtfully designed to maintain a contamination-free environment throughout the entire process. Here we perform Benedict's, lean hydrogen, and UV fluorescence tests to detect the presence of carbohydrates, proteins, and chlorophyll. We employ a custom-built Raman spectrometer to aid the onboard analysis of the collected samples. The in-house built science arm was engineered to optimize the sample transfer process for onboard analysis while ensuring zero contamination. For soil collection, we utilize a custom-designed regolith collector which ensures samples are gathered at a constant depth of 10 cm and stored without contamination for further analysis at the base station. The caching system features a quick release mechanism. All data streamed from the rover, including sensor readings, spectrometer results, and camera feeds, are seamlessly integrated into a centralized science dashboard. We perform 3 rapid chemical tests to support our hypothesis of past microbial life. The Molish test detects carbohydrates, producing a characteristic purple ring when positive. The Butyr test turns purple in the presence of proteins. All the tests are selected keeping in mind that no external heat is required. The results are cross-referenced with onboard sensor data to validate our findings and reinforce the mission's evidence of potential ancient life.
For real-time data transmission, we utilize a 915 MHz directional and omnidirectional antenna on the base station to communicate with the rover up to 2.5 km. Additionally, a 5.8 GHz communication system is employed for real-time video transmission.
Our electrical system now features a discrete power supply system architecture, enabling selective shutdown of individual rover subsystems. We can now shut down a specific subsystem like the drive system with shutting down the main control and telemetry system. We have upgraded to a 24-volt lithium-ion battery pack equipped with a customized battery management system module, allowing remote monitoring and emergency shutdown from the base station. This ensures a continuous runtime of up to 2 hours. The BMS can communicate with the base station through the rover onboard telemetry system. A customized power distribution system maintains stable voltage levels across all terminals and keeps the system steady. In Axios, all of our MCUs, motors, and actuators communicate over canvas, which helps us reduce and simplify system wiring. To enhance reliability, we have developed custom brushless motors paired with distributed motor drivers on each motor, reducing the risk of drive failure on a concurrent mission. The system also includes primary and secondary customized motherboard PCBs along with a swappable mission-specific daughter board. This modular design allows rapid transition between mission and simplifies system configuration procedures. For safety, an integrated kill switch provides immediate shutdown capability in emergencies.
For the autonomous mission, we have developed a custom nav to stack incorporating behavior trees for complex decision-making such as handling cost map clearing, path replanning, and failure recovery. We have optimized our system for reliability and efficiency. To achieve precise GPS navigation and accurate localization, we fuse data from wheel encoders, differential RTK GPS, and IMU using the extended Kalman filter algorithm. Custom-made algorithm detects 2 arco markers to find the entrance of the lava tube, and the distance is measured from the odometer, which is sent back to the base. 3D point cloud mapping and LiDAR are used for multiple purposes, like the real-time obstacle detection and avoidance.
The peak of a specific area is detected through the point cloud map and GPS altitude. The custom gripper is fabricated to hold the antenna and drop it on the peak point. With a depth camera and a custom algorithm, the rover detects and avoids potholes. To find the coldest point, we are using a temperature sensor. The rover performs spiral search while measuring the temperature and keeping track of the GPS coordinates. When it traverses the whole area and finds the coldest surface, it transmits the GPS coordinate to the base station. Our dashboard displays key mission data including mode status, traverse path, goal distance, and detected markers. All processing runs on the Jetson AGX Orin, ensuring high-performance autonomy in challenging environments. To ensure smooth operation during the night mission, 2 floodlights have been installed on the rover, one at the front for navigation and another at the rear to assist with reversing. The rover is also capable of towing 4-wheeled carts weighing up to 30 kg. Additionally, it can handle cable connections with ease, enhancing its overall operational efficiency.
With Axios, the UIU Mars Rover team continues to push the limits of student-led space robotics. From advanced mechanics to intelligent autonomy, every system reflects our passion, innovation, and teamwork. As we face new challenges and competitions ahead, we remain driven to learn, grow, and make lasting impact in the field of planetary exploration.